Hey, year 12. Got 4 people watching. Hey, Winkit. Thanks so much for coming. It's great to see you. I hope you're well. I feel like I haven't seen you guys in ages. Hey, Donna. Thanks for coming. Hola. So everyone's well, and I'm glad to hear it. Have you guys had a chance at filling in the document with your scores that you got on the papers that I sent you? If you get a chance, just try and fill it in before the end of the holidays. I'm going to be going through just paper 1 today. I'm hoping to take less than an hour and a half. I know that the paper is an hour and a half. Hey, Kayan, great to see you. I'm going to be as quick as possible going through it, but I know that it tends to take longer going through a paper. So I'll do the best I can at trying to get it done within the hour. Okay, I think we should crack on since I don't think many people are going to be here today. Okay, right, hide that bit. Okay, so October 2018. So let's have a quick look. Right, I've also taken the periodic table out of your sorry, moving all this stuff out of the way. I've taken your periodic table out of your data booklet just so I have it on hand because it might be useful. But I'm going to start straight off. This is Mr. Duncan's. I'm actually going to lay my tablet completely flat. So surname is Duncan. First name's Toby. Okay. Right. So first question is a simple balance equation. Oh, interesting one though. 1 silicon, 2 oxygen. I'm going to skip the oxygens for a moment. Going to go for the Fs. You kind of get used to this whole idea of picking and choosing the people that you want to balance first. I just happen to see the Fs and figure there's quite a high number of those on that side, so it might be easy to balance that side first. In terms of oxygens now wise, see now that if I now do a 2 there, that's now going to balance out because I've now got 2 and 6 hydrogens, so that now all adds up. So our ratio is going to be a 1 to 3. Or 3 to 1. Now that's very interesting. Hey Ria, thanks for coming. Great to see you. That's a great question, isn't it? Because I think a lot of students are going to think, well, hang on a minute. I'm looking for a ratio of 6 to 2, but they've then simplified it. What a lovely extension on GCSE. That's a really, really lovely question, that one. And I think a lot of students might be freaked out by it and look to go for the 6 to 1. That's the only option I could see students wanting to take. But that's a 3 to 1 ratio on that one. Okay, next. For safety reasons, the concentration of lead paint should not exceed 600 parts per million. Everyone hates ppm questions. Hi, Nikita. Thanks for coming along. Good to see you. Therefore, the mass of lead in 1 kilogram of paint should not exceed, right. So parts per million questions are rather lovely questions. So what we want to do is we want to say that we've got, the question is, what is our million? Yes? Who is Savior Sword? I don't know who that is. People use ridiculous names. It becomes difficult for me to be able to know who it is. Is it Ivan? I don't know. Yeah, who's Xavier Sword? Right, so the million in this case, so my million is my 1 kilo. Yeah, so I've got parts per million. I need 600. I need 600 parts per million. So what that means is my million is 1 kilogram, which is 1,000 grams, because you notice that my answers are in its 10Z. So we've got, so what I now need to do is, I now need to have this as a multiply or divide by 600, don't I? Divide by, to get my parts per million. Oh, I hate parts per million questions. So if we go, do you know what? I'm going to do a rather odd thing here. I'm going to go from top to bottom. So 0.06 grams. What's the multiply factor there? Because 1,000 grams is my million. 1,000 grams is my million. So 600 parts per million. Divide it by 600. No, that's not going to work out. Where's my calculator? I've lost my calculator. Found it. Okay, there we go. Right, so what's that going to be in parts per million? So to get from there to times 1,000, yeah? So if I times that by 1,000, 0.06 times 1,000 gives me 60. That's 60 parts per million. Yeah? So what's then 0.6? That's going to be greater. Yeah? So to get from 1,000 grams to a million is times 1,000. So I'm going to go times by 1,000 again. So so that's going to be 6 parts per million. That's definitely not going to work out. Oh, isn't that interesting? Oh, have I done? I mean, I made a mistake. Oh, yeah. Hang on a second. No, I tell her. Yeah. Oh, 600. Oh, okay. So then 6 grams. That's going to be 60. Oh, hang on. So what was that first one? 0.06 times 1,000. 60. And then 0.6 times 1,000 gives me 600. That's 600 parts per million. Sorry, my bad. There's 600 ppm. It's that one. It's B. So parts per million, even I don't like them because I feel like there's this, you need a bit of kind of, you need a process in here to help you figure that out. They have said that 1 kilogram is our million because it's part per millions in 1 kilo. So how do I get from 1 kilo to a million? And that is times by 1,000. Agreed? Yeah. So now once I've got that per million, in order to get these into parts per million, I'll do the same thing, multiply these by the same multiplying factor, and I get B as 600 parts per million. That is not, there's going to be a way around that to do that in an easier method, but I don't like trying to reteach it. I feel like I'm just going to run each one of them. I do apologize. I probably want to do some more questions on parts per million. The solution contains the greatest number of chloride ions. Right, so chloride ions, we know that aluminium chloride is going to split off to give us 3 Cl minus. Magnesium chloride is going to split off to give us 2 chloride ions. HCl is going to give us 1, and calcium chloride is going to give us 2. So the next thing is, now we've got moles, we've got a volume and a concentration. So now what we need to do is, we now need to multiply these both by their concentrations, all by their concs, in order to be able to get which one actually has the highest number of chloride ions per volume. So we've got number of moles is C1 exponential minus 2 times by 10. That gives me 0.1 times by 0.1. And then we get 1.5 exponential minus 2 times by 20. That's 0.3. 0.3. And then I have 1.5 exponential minus 2 times by 30. Gives us 4.5. Just going to check that one again because I typed it into my calculator wrong. Exponential minus 2 times by 30 gives us 0.45. Do apologize. I knew I typed it into my calculator wrong. And then I'm going to get 10 times 2.5 exponential minus 2 gives us 0.25. Right, I'm now going to multiply these by the number of chloride ions that each one gives us. So this one's easy because that one's the correct number. Yeah, that one's correct. This one's going to be double it. So I'm going to double that to 0.6. Going to triple that to 0.3. Going to double this one to 0.5. So the highest one is going to be B. I hope that makes sense, folks. Hey, Emma, good to see you. Thanks for coming along. So B is my answer. Next, which statement is true about the ions? Oh, interesting. Magnesium 55. Oh, it's giving us the mass, and so we can work out the M over Z, folks. That's a lovely mass spec question. So the M over Z is going to be 55 divided by 2. So that's going to be 27.5. And then 56 divided by 2 gives me 28. So the one that's going to be deflected the most is that one. So it's going to be deflected less than that one. That is not true. No. They have the same number of electrons. Ooh. Are they right next to each other on the table? I doubt that then. They're 55 and 56, but they're mass numbers. Ooh, I need to check my table. Hang on a minute. Manganese is the one next to it. It is. So 25 and 26, 2 plus and 2 plus. Nope, still not the same number. I'd have to have it with different numbers. Next, that's not correct either. Has more protons? No, because that's number 26. That's number 25. So that's not correct either. they have the same number of neutrons. Ooh, is that really correct? Same number of neutrons. So we're going to have, if that one's 20, element number 20, 26, is that right? Element 26 for iron? Come on, laptop, going slower than I am. 26 and 25. So what I'm now going to do, 26 and 25. So minus them is going to be 30. So the last one, D, is the correct answer. Next, 5. 10 centimeters cubed solution needed to be diluted to make a concentration. Ooh, C1V1 equals C2V2. That's a nice one. Yeah, so as soon as you see the word dilution, this is where this equation comes in. This is the dilution equation. I hope you guys have been taught it by your other teacher. So the original volume was 10, and the original concentration is 1 times 10 to the minus 2. So, and that's going to equal a new concentration of 5 times 10 to the minus 4 and times by a new volume V2. Reorganize it. 5 times 10 to the minus 4. It's going to give me the new total volume. So 1 exponential minus 2 times by 10 divided by 5 exponential minus 4 gives me a new total volume of 200. Well, how much did I start off with? I started off with 10, so I need to add 190. So let's see. Next. Avogadro's constant is this, 6.022 times 10 to the 23, the number of atoms in 15 grams of nitrogen monoxide. It's a trap. I hope you all recognize that immediately, because in each molecule, of course, is going to have, it's got 2 atoms. So what the first thing I can do is I can go number of moles is grams over rams. That's the first thing I've got to do. 15 grams over the relative molecular mass of nitrogen monoxide, which is 14 plus 16, which is 30. Okay, so that's going to give us 0.5 moles of NO. But then, how many atoms do I have? I need to double it. That's 1 mole of atoms. The reason being is that that's if that's 0.5 moles of that guy, and that has 2 atoms per molecule, I've got 1 mole of atoms, which is going to be 6.022 times 10 to the 23. So the answer is going to read B again. Next. Question 7. Nitrogen monoxide reacts with oxygen to form nitrogen dioxide. 200 centimeters cubed of nitrogen monoxide is mixed with 350 centimeters cubed of oxygen. What is the total volume in centimeters of the gaseous mixture when the reaction is complete? All volumes are measured at the same temperature and pressure. Right, we know that number of moles is V over 24, and we know that all gases, no matter who they are, the volumes are the same. So we can use the volume directly as moles as long as we can say that they're proportional. Agreed? So what we can do is, the problem is there's a ratio in the equation. I don't like it. What I'm going to do is, I'm actually going to do this the long way, and I'm going to say, right, I've got 200 centimeters cubed, so V over 24. It's actually over 24,000. Hang on, sorry. Playing around with the laptop. 200 centimeters cubed divided by 24,000 gives me the moles of nitrogen dioxide, which is 8.10 to the minus 3. And then I go, the moles of oxygen is 350 divided by 24. Sorry, my other laptop's causing me problems. 350 divided by 24,000 again, because I'm in centimeters cubed. That's going to give me it's giving me a normal standard. Don't like it. 46. I'm actually going to go 8.33 exponential minus 3, and I'm then going to go shift N just to take it out. I've got 0.00833 of that guy. Wow, okay, so I've got a tiny amount of that. Yeah, so who's in excess? And it's in a 2-to-1 ratio. Got to watch out for that. Let's cover somebody up. Let's just make that disappear. So I need half of that amount. Divide that by 2, which is going to give me, I feel like that's not right. 200 and 350. Have I made a mistake here? 200 divided by 24,000. I feel like I've made a mistake. And then 350 divided by 24,000. I feel like I've made an error. No, I haven't. It's the same number. Okay, fine. So if I go from there to there, yeah, I actually need 0.00833 divided by 2. I actually need shift N, I actually need 0.0041765 of that guy. Wow, okay. So I'm actually going to produce very little of this. So what that means is I'm actually, oh, right, hang on a sec. So I now realize that this one here is in excess. That one is in huge excess. No, it's not. I tell a lie. The oxygen is in huge excess. This is in massive excess. So all of that is going to become nitrogen dioxide. So I'm going to end up with a final balloon containing NO2, and that number there will be 0.00833 because it's in a 1-to-1 ratio, 2-to-2 ratio. I'm then going to have left over oxygen. So the question is, how much oxygen am I going to get left over? So I'm now there's going to be a really easy way around this, folks. I'm doing this the ridiculously long way. It's because I work in moles. I do apologize. So, okay, how much is oxygen's left over? Well, it only needed half of it, didn't it? So, oh, well, hang on a sec. We can do this more easily. I'm going to end up with, let's treat the volumes now. That volume there is that volume. So I've got 200 centimeters cubed of that guy. But then that number there is that number. I have got 350 is that many moles, but I'm going to actually only reduce that by half. 0.00833 divided by 2 gives me, right, that much. So hang on a minute. That there is going to lose 4.165 times 10 to the minus 3. Right. You realize that it's proportional to it, isn't it? So 0.0146 minus answer gives me 0.01043 of oxygen left over. That's the excess. Well, what percentage of that is it? I'm going to have 200, well, it's not going to be A, is it? The answer is most of it. Take 350 divided by 0.0146 and then multiply that by 0.0104. I have 250 left over. I've got 450. The answer is C. Hi, Sherlyn. Nice to see you. Thanks for coming. Guys, that's a really, really hard question. I wanna try and do this in a simpler fashion. Let's simplify this. Gases are horrible. Because what we can say is that all gases measure the same. So we can say that I have 200 of this at the beginning and 350 of this. Right, so the first thing we realize is that I'm going to create, because this here is in massive excess because of the ratio of 2 to 1 to 2. Agreed? This is in enormous, this is in enormous excess. So what that means is, yeah, so we can go, right, 2 moles of this react with 1 mole of that. So what I'm going to make is, out of these 200, this is where I need to use all my colors, that 200 is going to react with only 100 of the oxygen. Agreed? Yes? Right, so what that means is I'm therefore going to make, I'm going to make 200 of this because the ratio of him is 2 to 2. So that is going to become 200. I'm going to use 100 of this guy. It was 350. I have 250 left over. Total volume at the end is 450. That's really hard. It takes practice. Please work on it. Next. By the way, I'm making a massive assumption here that I'm getting all of these right. Please let me know if I get one wrong. The first 6 successive ionization elements of X. Right, okay. So we've got small, 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 small. Whoa, massive. Right. So it's in group 4. So if it's in group 4, it's going to be either +2 or -2. No, sorry. +4 or -4. It's in group 4. Yeah. By the way, what this shows us is it shows us the energy it takes to remove the electrons. There's my jump. It has 4 electrons in its outer shell. If it reacts with oxygen, it's going to be +4. So it's going to be him, because the oxygen there, that there is O2 minus. There's times by 2 of them, which gives you -4. X is in a +4. That's me. I'm A. Please do let me know if I get anything wrong. Next, total number of occupied orbitals in the third quantum shell of the silicon atom in its ground state is, wow, what a, by the way, if that isn't something like, guys, I've not taught you all this, you should be looking at that thinking, WTF, what the food, yeah? So total number of occupied orbitals, right, in the third quantum shell, so third shell. Don't overthink it, folks. Yeah, so hang on a minute. Silicon is element number, it's below carbon, 28? Oh, hang on. I don't know what silicon is. Silicon is element number 14, mass 28. Silicon is number 14. So let's write its configuration out. 1s2, 2s2, 2p6, 3s2, 3p2. Is that correct? It's element number 14, 10, 14. That's correct. Right. Total number of occupied orbitals in the third shell. So hang on a minute. Let's turn this into boxes. Occupied orbitals. Oh, there we go. There we go. Occupied orbitals is 3. So it's B. Please, I'd like to think, Winkit, can you do me a favor? Can you check that I'm getting these right, please? That I've made no mistakes so far. That'd be very much appreciated. Next, which of these statements is correct? The ionic radii of an alkali metal increases down the group. The ionic radii is absolutely correct. Alkali metal increases down the group. It's totally true. Because we know that we're going to start off with a periodic table, spend the whole time at the periodic table. No problem. Thanks, Winkit. Alkali metals. Here's the atom. Here's the ion. 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 It is increasing down group. That is correct. It's not incorrect there. I'm just going to check that the rest of them are all rubbish. The ionic radii of these increases. No, that's not true. Sodium plus, magnesium 2 plus, aluminium 3 plus, tiny aluminium 3 plus. That's not right. No. The first ionization energy of the alkaline increases. Nope, that's not true. The outermost electron, as we go down the alkali metals, yeah, they get bigger. So the electron's further from the nucleus. It's going to be easier to remove it. So it's going to increase. So it's going to decrease down the group, not increase. So that's garbage. The melting temperature of the most successive elements in period 3 always increases across the table. No, that's not true at all. The melting across period 3, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. No, it's complete garbage. We know that one. That's not right either. So the answer was A. Smash that straight off the bat. Which compound would be expected to show the greatest covalent character? The ones that are going to be closest on the table. So lithium and bromine are miles away. Probably not. Lithium iodide. That one will show more covalent character than that guy. Whoa, fluoride is tiny. It's B. We're done. So the answer is B. Now, students are going to go, how did you know that? Yeah, mean beans. Hey, mean beans. That's Ivan, isn't it? People are going to say, how do you know that? Okay, so lithium is small, bromine is big, so it's going to get distorted quite heavily. Yeah, but then there's lithium iodide, same small, but this time it's enormous. Remember, the bigger the negative ion, the more distortion it's going to have. So that one is more than. Then we've got potassium. Potassium is bigger than lithium, and fluoride is tiny, very little distortion. And then same thing, that's going to be potassium and a slightly larger chloride. It's nowhere near. This is the smallest positive and the biggest negative. So that one's got the most covalent character. So that's B. Next. Right, phosphoric acid. Okay, 2 steps. What is the percentage atom economy? It's 100%. Lol! Ha! It's 100%. Isn't that hilarious? There's no byproduct. There's no waste. If I put in 5 of these, I will make 5 of these. 5 of those go in there, and I then make all of these. There's no other product. The answer is 100%. Wow, that's clever. No waste, because that cancels. Look at the equation. The overall equation, P4 plus 5 O2s plus 6 H2Os, and I only make one product. There's H3PO4. That's 100%. No other waste. Wow, great question. Talk about doing that in 1 second. That's nice. God, if you got lost on that, folks, you'd be lost in it for a while. 13, this question is about ionic equations, right? Who's doing what? Right, number 1 is chloride spectator. Yeah, because it's aqueous. Yeah, so that's going to be H plus going to nickel 2 plus. Yeah, anyone else not changing? No, everybody else is changing oxidation state or doing something. Yeah, everything else. There's a change in state in everything. Right, so that's it. So the answer is A. Ugh. Is that correct? It's definitely not this. It's definitely not that one. Or that one. Or this. It's not that one. See, the carbon dioxide has vanished. Yeah. It's not that one. Because why would the Cl be in there? No. And then the Cl's in that one as well. It's not doing anything. Cl shouldn't appear in them. Cl should just disappear. It's not changed. Cl's in a -1 and a -1 having spectator. A. Next. Excess hydrochloric acid reacts with 0.2 moles of nickel 2 carbonate. Excess hydrochloric. Okay. What is the volume in dm cubed of gas produced at room temperature and pressure? Assume, oh wow, 1 mole of any gas occupies 24 dm cubed. They shouldn't do that. They should be giving you PV equals nRT. They should be just giving you the ideal gas constant. That's not going to be done anymore, folks, although Edexcel do seem to be blending them a little bit. It's a bit weird. Right, they've given us the equation, yeah, which is nice of them. They have said excess hydrochloric acid reacts with 0.2 moles of nickel carbonate. What volume of gas? It's a 1-to-1 ratio. I'm going to make 0.2 moles of that. Right, V over 24. Number of moles is V over 24, and they want me in dm cubed. So bring that over there, times by 24. So 0.2 times by 24 gives me 4.8. Yeah, there's C, 4.8. Next, what is the minimum volume of hydrochloric acid with a concentration of? To react with, okay, so that's just the standard titration question. Yeah, so they've given you 0.2 moles of him, and what do they want? The volume? Was the minimum volume of 4 molar. Okay, so that there is 4 moles per dm cubed. Okay, well, the ratio is 1 to 2, so I need to double that to 0.4 moles. It was the same numbers, wasn't it? Yeah. And then reorganize C times V over 1,000. Number of moles equals C times V over 1,000. Yeah, to give me the volume in centimeters cubed, because that's what they want. Yeah, reorganize. Times by 1,000 all over the concentration of 4. Right. And that's going to give me my volume in centimeters cubed. So the moles, which became what? 0.4. 0.4 times 1,000 divided by 4 is 100. So it's C, 100 centimeters cubed. Next, when 100 centimeters cubed of 2 moles per dm cubed sodium hydroxide solution is added to 100 of an excess form, the temperature rises this. Energy transfer is this. What is the enthalpy change for the reaction? Oh God, we're even making you just not even a number, just an equation. Right. So we know that Q equals mc delta T. That's what we know. T is there. Yeah. The 4.2 is that, and then we also know that delta H equals Q over N, but we need to make sure that there's a times 1,000 in here step, folks. Yeah, because we're going to have to know that Q, to get from there to there, you've got to divide by 1,000. Agreed? So hang on a minute, let's then input my numbers. That's a fascinating question. Input the numbers, the mass of the solution, the total solution volume, 100 centimeters cubed. Yeah, is added to. So that's 200 multiplied by 4.2 multiplied by a temperature change. Yeah. And then that one is going to be divided by the moles. Well, hang on a sec. So we now realize that we can then write this down as delta H equals, because Q is equal to all of this stuff. So we can do delta H is equal to 200 times by 4.2 times by 12.5, but there should be a divide by 1,000 here over the moles. There's a really weird thing here, folks. Oh, and don't forget that the temperature rose, so it must be negative. They're all negative, though, do you notice? Yeah. So then we need moles. Well, moles, it said the sulfuric acid is in excess. So we need to do moles, is that one, C times B over 1,000. So number of moles is C times by V over 1,000, because I'm in centimeters cubed. 2 times 100 divided by 1,000 equals 0.2. So what I don't understand is how we're meant to get, where's the 1,000 disappeared to? So by the way, the answer is 0.2. So what I want to choose now, folks, what I want to do is put 0.2 there. What was the ratio? Did it matter? No, it doesn't matter, because it was in excess. Or does it matter? So what's really strange is it's either C or A, even though my number's not going to be out, because what is the enthalpy change in kilojoules per mole? It's not right. It's always going to be out. None of them are going to give me that. They're going to give me in joules per mole. It's really strange. I don't quite understand that. Mass in grams. It's really weird. Anyway, 2-to-1 ratio. The answer's A. No, it's the answer's C. It's C. Winkit, can you quickly check? Is 4, that's the first one I feel like I want to check. Is it C? I don't really want to erase it, to be fair. Is the answer C for 14? First one I feel like I want to check. Wow. It's taking me to 14 on the multiple choice before I want to check a mark scheme. Am I correct with C? Check me. 14, C, please. Check me. C. Cool, okay. Thanks, Winkit. Really helpful. Next, hydrogen is manufactured by the following reaction. The percentage yield is 90%. The mass of hydrogen in tons, that can be produced from 160 tons. Well, that's nice, isn't it? 160 tons of methane. So 160, if you put it in tons, it comes out in tons. Yeah? So I'm going to go from there to hydrogen. It's a 3, so grams over rams. So 160. So you can't use the equation unless you're in moles. Number of moles is grams over rams. Well, if I put in tons, yeah, it doesn't matter because I don't need the real number. I just spit it out in tons again. It's not really such a big deal. I just put in tons here. Yeah, so I just do 160 over the MR of methane, which is 16, and I get 10 moles. Right, from there to there is a times by 3. So I'm going to get 30 moles, yeah, of hydrogen. Then multiply it by 2 to give me, I should multiply that by 2 to give me 20 tons. What? How did that happen? 30 times? What happened there? 10 times by 3 gives me 10 times by 3 gives me 30 times number of moles. I shouldn't do it. Moles is grams over rams. Yeah, multiplied by 2. So times by 2 gives me 60. How did that happen? Gives me 60, but then I've only got 90% of it. So multiply that by 0.9. So times by 0.9, and I get 54. The answer is B. Next, C How am I doing for time-wise? 35 minutes, still on multiple choice. What is the systematic name for the monomer formed from this? Right, just put the double bond back. Yeah, C double bond C. So I've got, oh, C2H5. That's clever, isn't it? Let's draw this out the way I want to. Yeah, and then there, and then there. Longest chain. Wonder who didn't get it. Yeah. So 1, 2, 3, 4, 5. So it's based on pent. It's an ene between 2 and 3. So pent 2-ene. And it's a 3-methyl. Who didn't get it? That's really clever. 3-methyl pent 2-ene. Winner! Cool. I like it. Here's a question for you guys. Does that show geometrical isomerism? Because I think it does. It's frustrating, isn't it? Don't even give the E or Z value. Annoying. The reason why you can't is because once it forms the polymer, the double bond vanishes, it goes into rotation, which means we wouldn't know which isomer it was that was doing it. Isn't that genius? The compound contains, give the empirical formula, percent to mass. Laura, don't know if Laura's here watching. I really hope she is. It'd be great if she was. Empirical never ends. I just gave a GCSE webinar where an empirical came up, and it's just nice to see the GCSE reoccurring, folks. Percent to mass, mass to moles, over 40.1, over 12, over 16, all 0.0s except for the calcium. So 31.25 divided by 40.1 gives me 0.779, and then 18.75 divided by 12 gives me 1.5625, and then I've got 50 divided by 16, which gives me 3.125. Divide them all by the smallest. Yeah, all by the smallest. Nothing changes. It's just GCSE 1. Well, that one's going to be 2 in it. 1.55625 divided by 0.779 gives me 2. Yeah, and then 3.125 divided by 0.779 gives me 4. Empirical formula is 1 calcium, 2 carbons, 4 oxygen, so it's A. I'm done. Next, which reagent reacts with butadiene to form a compound with the formula shown with that one? Yes, ene to diol, acidified potassium permanganate, and we're done. How cool is that? You just got to know your transformations, folks. You've just got to know them. That's 1 mark, 1 second. I'll take that. Next, right. Use the data to calculate the sample of zinc has been a relative atomic mass of. Calculate the sample contains 4 isomers. The abundance of 3 of the isomers is shown below. Use the data to calculate the relative isotopic mass of the 4. Wow, nice. So we know that relative atomic mass is equal to isomer. Okay, I'm not going to bother with the teaching bit. I'm just going to go through the answer. So we know that 65.44 equals 64 times by 49 plus 66 times 27.9 plus 67 times 4.5 plus x multiplied by, right, we need to work out its percentage. We can do that. For 100 minus 49, so 100% minus 49, the percentage of that guy, minus 27.9, the percentage of that guy, and minus 4.5, that guy. So minus 27.9 minus 4.5. First mark is 18.6. First mark is there. Right. All of that is over 100. Cool. Right. Let's do some cool mathematic rearranging. So first thing, bring the 100 over. 6,544 equals, let's start multiplying these brackets. So let's just get rid of all these brackets. 64 times 49 gives me 3,136 plus 66 times 27.9 gives me 1841.4 plus 67 times 4.5 gives me 301.5. plus 8, A plus 18.6x. Right, let's sum all these up. 3136 plus 1841.4 plus 301.5. Total of those guys, 6544 equals 5278.6 plus 18.6x. Bring him over to there. Right, minus it. So 6544 minus answer, which is already on my calculator. So 1265.4 equals 18.6x. Divide everything by 18.6 and I get the value of x. So divide that by 18.6 and I should get a whole number of 68. The answer, divide that by 18.6 and I get an answer of 68. And there's my answer. It gives it, says, give your answer to the appropriate significant figures. And the answer is, it's a whole number, folks. How many people are going to do that? You're about to lose it. The reason being, folks, is we're calculating that look at the relative isotopic mass. You can't have point value of a neutron. They're all whole numbers. All isotopes would be. That's why the GCSE periodic table is whole numbers, because they're just quoting the most common isotope. Yeah, so great. That is an outstanding question, all for 3 marks. How mean. State and explain what difference, if any, you would expect between the chemical properties of the lighters and having none. No difference. No difference in chemical properties. Yeah, because they're isotopes. No different in chemical properties. They've got the same number of electrons. And that's the real answer. No difference in chemical properties. Yeah. We know that the reason what decides the chemical properties are your electrons and their configuration. Well, they've got the same number of electrons, therefore they have the same chemical properties. Next, isotopic masses are determined using mass spectrometry. The sample under the investigation is first converted into gaseous ions. Ions are passed through slits in a series of charged plates. Give 2 reasons for this procedure. Huh. Wow, I have never seen this question. Ever. They've never done it. Ions are then passed through a series of electrical charged plates. Give 2 reasons for this procedure. Huh. Okay. So this, oh, hang on a second. This is ionization. Oh, hang on a minute. No, they're determining the sample under investigation is first converted into gaseous ions. Ions are then passed through slits in a series of electrical charged plates. Right. What are the slits for? The slits produce a beam of ions. Yeah, they're producing a beam of them. Rather than having just a whole host of them there, you need a beam moving in one line. Yeah. Slits produce a beam of ions. Single file. The second thing is charged plates. This is acceleration. Charged plates accelerate the ions. Wow, I need to check that. 2 marks. Doesn't seem like I've written very much. Yeah, the slits produce a beam in single file. They all the ions are literally in a 1 atom thick line. I just wonder how far they want me to go with that. I need to check the mark scheme for that one, folks. That one's kind of important. I don't know where I've got this. Hang on a sec. I've got it down here somewhere. Hang on. I'm going to check that mark scheme. Let's have a quick look. Paper 1 mark scheme. This is the first one I really, really want to see what they've actually written to say that I've got the right. Number 1, to accelerate ions. I like it. I'm happy with that. And it's a 1L because I'm an idiot. Yeah, to accelerate ions. Yeah, the next one is to select ions traveling in same direction or same to produce a fine beam of ions, a focused. That's really clever. Cool. I like it. To produce a beam of ions. I got both marks. I'll take it. Next. State how ions of different masses are separated. They're deflected differently. Oh, do I want to say that? How are they separated? Using a magnetic field. Using a magnetic, oh my goodness. Using a variable magnetic field. Yeah. So that's how they're separated. Oh, what does the box cube say? Using a magnetic field. Fine. Okay. No. I was really stumped for a minute then. The ions eventually produce a current in the detector. The data from the detector will produce mass spectrum. State how the horizontal axis is labeled. Give your answer in words, not symbols. State how the horizontal of the mass spectrum, it's mass in words. Mass over charge. How bizarre. Don't know if that's right either. Complete the electronic configuration of zinc. An atom of zinc. Right, got to use my table now, folks. I do the same method that I've been doing for GCSE. You read it left to right. We're going for zinc. All the way to the top. Jam on. There we go. Right, we're going to read off zinc. Okay. Going to read off zinc. 1s2. 1s2. 2s2. 2p6. 3s2, 3p6, 4s2, 3d10, and we're done. There's an atom of zinc. Right, let's go all the way to the end. Come on, computer. There we go. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10 for zinc. Next, describe with the aid of a diagram the bonding in a sample of zinc. You should state the attractions that hold the particles together. I like it. So zinc, by the way, all transition metals, zinc especially, forms a 2+, Zn2+, Zn2+. Going to draw 6 particles in metals, Zn2+, 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 Zn2+. Right, how many electrons? 2 per atom. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I like it. And so we're going to have the electrostatic attraction. The electrostatic attraction between the giant lattice of cations, this is the GCSE explanation for metal bonding, by the way, giant lattice of cations, and the C of delocalized electrons. And we're done. I wouldn't do that E- in an exam, so please don't do it. I won't do it either, in fact, it's a bad habit. Electrons, C of delocalized electrons. Next, doing well. Next. Oh, good old successive ionization energies. Oh, the second ionization energy. Oh, that's mean. The second ionization energies are shown on the grid. Oh, I don't like it. I don't like it, folks. Mark and the values for sulfur. Right, so phosphorus, sulfur. There you go. It's going to be in a straight line. Yeah, there's sulfur. Next, write an equation including for the second ionization of aluminium. Second ionization of aluminium. Al1 plus gas going to Al2 plus gas and 1 electron. I like it. Who's going to forget their state symbols, folks? Anyway. Explain why the second ionization energy of aluminium is greater than both the second ionization energy of magnesium and the second ionization energy of silicon. Right. That's a long question, that. How many marks is that for? Okay. So aluminium's second ionization energy is higher than magnesium because it has one extra proton, but same shielding. Right, let me just tell you why, and that they're gonna put a big fat thing saying that you have to say the word sane. The reason why is because the second magnesium was 1s2, magnesium element number 12, 1s2, 2s2, 2p6, 3s2. Right, there's Mg atom. Here's an Mg1 plus ion. Yeah, here's the 1 plus ion, 3s1. There's Mg1 plus. We're going to have to remove that electron. Let's look at aluminium. So aluminium is, I'm just going to underline that, 1s2, 2s2, 2p6, 3s2, 3p1. There's an aluminium atom. But then the aluminium 1 plus ion is going to be 1s2, 2s2, 2p6, 3s2, and then that element's gone. So it's got the same shielding, yeah? That's an Al1 plus ion, the same as the magnesium. The electrons are in the same subshell, same orbital, which means it's going to have exactly the same shielding, but it has an extra proton. We're done. What about silicon? Now, silicon, of course, is different because silicon is element number 14. Is that right? Yeah. Silicon, yeah, something like that. And then we've got 1s2, 2s2, 2p6, 3s2, 3p2. Is that right? For silicon, I need the table. Where's my table? 3p2, yeah, same, I like it. So there's a silicon atom, and what does the silicon 1 plus ion look like? It looks exactly the same, but it has 3p1. What that means is you're still removing an electron from a subshell further out. So that one's going to be lower. So one extra proton, but same shielding. Right, so Al second ionization energy is higher than silicons, than Si, due to silicon having outermost electron in 3p subshell compared to Al with outermost electron in 2p. Silicon has greater shielding. Easier to remove. So easier to remove. Ooh, that's hot. What a long-winded process that is. God. Oh. So to get the other mark in that, I bet I have to say aluminium outer. I'm going to say, just to say this is a tack on, aluminium's electron is in the 3s, and magnesium's are also in the 3s. Same subshell. That's probably going to be the other mark. Predict with reason which element in period 3 has the highest second ionization energy. Oh God. Hang on a sec. Highest second. Well, the problem is this graph would actually then do this. Like that. Yeah, but then that there, because we've got sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine is a dip, and argon. And argon's higher, but sodium's is going to be up here. Yeah, because we're moving it from a shell further down because we're in the second. So the answer is sodium. It's a trap. Yeah, I hope you guys got that. That's tricky, that. Easy to make that mistake. Predict with a reason. Sodium. Sodium, due to having to remove electron from, it will be from the 2p subshell. Cool, close to the nucleus. Next, magnesium and sulfur both react with chlorine to form chlorides with a formula of XCl2. Consist of covalent. Describe how the electrical conductivities of these two compounds differ. Huh, fascinating. So MgCl2 will conduct electricity when molten or in solution, but not in solid. SCl2 will not conduct under any conditions. Will not conduct in any state. You're done? Clever. Got an awful lot for 1 mark. Draw a dot and cross diagram for sulfur dichloride. Okay. So SCl2. Pretty standard. A very standard question. I'm quite happy with that. Sulfur's got 6. This is very similar to most things. This is easy. Oh, it's really easy. Sulfur dichloride. Wow, that's like the easiest one I have seen. I'm going to actually switch those for X's, even though they wouldn't care in reality. Sulfur, there we go. Not complicated. Sketch an electron density map of sulfur dichloride. Ooh, an electron density map. They're wanting electron density map. I think they're going to want us to show the fact that chlorine's more electronegative than sulfur. Where am I? Where's my periodic table? At the back. Right. Sulfur and chlorine, they're very similar. But it certainly is going to be going towards the chlorine. So I need to try and find the page I'm up to. There we go. So what I'm going to do is I'm going to do sulfur and chlorine. And I'm going to do something like that. Want to see a mark scheme for that, folks? Definitely. Holy moly. Again, I haven't needed the mark scheme much, but that one, definitely want to see what they want for that. It's wanting them to show the fact it's polar. Fascinating. Oh, okay. So they're just wanting to draw at least 3 contour lines. Wow, interesting. They don't want to show any, they just want it to show you that it's bent. And it's only 1 mark. Interesting. So they wanted you to show at least 3 contour lines for each of them. Oh, eek. There we go. How fascinating. Draw with at least 1 contour line going around all atoms. Okay, fine. Interesting. It's showing that it's covalent, folks. State how the electron density map differs from that. Right, so they're going to have no overlap. Yeah. No. Hang on a second, sorry. No overlapping, because it's ionic. No overlapping contour lines. Yep, and there's your mark. I like it. If you're interested in knowing what that would look like, yeah. So it becomes Mg2 plus and Cl minus and Cl minus, of course. So you're going to end up with this will have partial covalent character. So we're going to have magnesium being 2 plus in the center, and the chlorines are going to be distorted, but no overlap. Yeah, but there is no overlap. They're just distorted. Yeah, to show you that it has covalent character. That's what it's going to look like. That's what the MgCl2 one would. Oh, are they asking us to draw it now? Guys, you can ignore this. You don't do this now until A2. Winner. So just ignore it. Right, that's really nice. That's now only A2, which is fab. That's where it should be. Right, okay. Good old Hess cycles, energetics. Right, the compound hydrazine is a liquid and used as rocket fuel. Right, so they've given you a cycle, they're making you fill it in. Right, so it says the standard enthalpy change of formation. Right, is that, and that? Right, so in order to complete the diagram, we need to put the elements, because it's formation, elements on the bottom, nitrogen, hydrogen, plus oxygen. Right, so to make hydrazine, from its elements to the compound, to make that is plus 50. And I'm making just one as a 1 there. Right, to go from here to oxygen, it doesn't exist because I'm going from an O2 to an O2. So I can ignore it. Don't need that. Can ignore that. Right, to go from there to there, don't need that because I'm going from nitrogen to nitrogen. Don't need that either. But I am going from down here to water. And I'm making 2 of them. So that's minus 285.8 times 2 because there's a 2 in there. Would everyone agree with this statement? Yeah. Donna, what about the lattice energy question? Okay, so Donna, you don't need to be able to do this yet. That now is A2 only. Is that all right? I can run it for you if you like, but you don't need it. It has been moved into A2. That one has in particular. I think. Did I teach you guys this? Okay, because I didn't know how to do it. Yeah, don't worry. You don't need it. I'm pretty sure that's been moved into A2. I'm tempted to check your specification. No. Okay. Good. Fab. Yeah, it's not on your specification now, so don't worry about it. Right, so now we want this one. So we need to go from here to here. The most important arrow in the whole of the cycle that way needs to equal that way. So this arrow is going against us. So I have got, so my delta H question mark equals minus brackets plus 50. People can say, why is it minus? Because the arrow, we're traveling in this direction. Yeah, and this arrow is going in the opposite direction to us. Yeah, so that becomes minus, it's going against us. And then this one's going with us. So plus brackets 2 times minus 285.8. Right, can I just point out, I'm about to lose a mark here. Did I balance the equation? I didn't. I would have lost a mark at that point. It came out in the wash, but I nearly lost it. You've got to balance the equation. It's got to be, that's really important. Right, so now we can just run that through our calculator. I'm literally going to type it in as I see it. Minus brackets plus 50, close brackets, plus brackets, 2 times minus 285.8. And I get minus 621.6. And there's my answer, folks. Just going to check that. Is that correct? Kind of want to know if that's the right answer. Not the correct answer. Yeah, 6.2. Oh, have I got a different number? What have I typed in? Have I typed in a different number here? Did I type in the wrong number? I think I may have. 8. Oh, that's strange. Why is that giving me a different number? Minus brackets 50 plus brackets 2 times minus 285.8. Why do I get a different number that's on the mark scheme? It's really strange. Oh, is it 50.6? Oh, stupid. So easily done. Oh, I'm such an idiot. Done it. So easily done. Minus brackets plus 50.6. That's really annoyed me. I think that's my first proper error there, folks. Yeah, definitely made an error. I would have lost a mark there for writing down the wrong number. Even me, guys, I never pretend like I'd get 100%. Yeah, I'd always make common errors the way that anybody does. Right, good old Bert. So it gives you the data. Calculate the enthalpy change for the laptop's doing something strange. Give it a sec. Sorry. Calculate the enthalpy change for the oxidation using the bond enthalpy values. Divided by 2. So we've got bond data is reactants minus products. Work these all out. So I have got hydrazine. Yeah, there's hydrazine. I'm drawing it out. This is important. Yeah. Going to N triple bond plus, I'm drawing it out so I don't make mistakes. Right, smash all the reactants. So I have got one N single bond, so that is 158 times 1. That's the N single bond. And then I've got NH bonds, and I've got 1, 2, 3, 4 of them. So the NH bond is 391 times by 4. And then I've got one O double bond, which is what? O double bond 498. 498 times by 1. Right, total all that up. What do I get? 158 plus 391 times 4 plus 498 gives me 2220. Right, there's reactants minus products. N triple bond is, wow, 945, and I've got just one of them. 945, and then I've got OH bonds, which are 464 times by 4. So I'm going to add those together. 945 plus 464 times by 4 gives me, made an error, 945 plus 464 times by 4 gives me 2,801. Right, reactants minus products, and 2 minus answer, and I get an answer of minus 81.0, and I'm done. Next, give 2 reasons why the enthalpy change calculated using bond enthalpy is different from the from the Hess cycle. Because, okay, so first reason is because these are mean bond values. Yeah. How different is it? Oh, isn't that interesting? When the Hess cycle is more exothermic. Mr. Duncan, are you going to do papers 1, 2, and 3 in one go? No way am I doing that. I'm going to do them one day at a time. I'm going to do paper 2 tomorrow, probably. 2 reasons why the Hess cycle differ. So number 1, the bond values are averages. The bond values are averaged over a range of compounds, averaged over a range of compounds. What's the next one going to be? That's really interesting. Give 2 reasons why the enthalpy reaction is different. 2 reasons. States. It's all in the question, folks. So the other reason is because bond enthalpies can only be taken from gaseous. Yeah. Number 2, bond values can only be measured from gaseous reactants, but hydrazine, N2H4, and H2O. Was it H2O as well? And H2O are liquids. There's your answer. Do want to check the mark scheme on that, though, anyway. Streaming marathon. No, that will take forever. Exactly. Never going to do that. That'd be madness. Total values, 0.0. I like it. And then I'm looking for bond energies are based on substances in gaseous state. Hess cycle is using values from liquids. And bond values are averaged over a range of compounds. I like it. Next. How are we doing? It's already been quite long, and I'm very aware of this. Is a long paper, actually. It's an hour and a half. See how we get on. I think I might have to do it in 2 parts. It is an hour and a half. Next, complete the curly arrows. I did say that this is the only one where you might actually get to see these half head arrows. That's awkward, isn't it? Next, write an equation, use it for the 2 propagation steps. Ooh. Right, reaction of decane in the presence of ultraviolet. So Cl dot plus C10H22 goes to HCl plus C10H21 dot on the C, then C10H21 dot on the C, reacting with chlorine to form C10H21Cl plus Cl dot. Write an equation for two terminations other than the one in which chlorine forms. Write equations using molecular formulae, okay, for 2 terminations other than the one in which chlorine forms. Okay, so C10H21 dot plus C10H21 dot termination, why not? C20 C20H42, wowzer. We're also going to get C10H21 dot plus Cl dot, not forming chlorine. Yeah, C10H. It's quite tricky after a while. You get Cl. There you go. The structure of decane is that. Write an equation for the incomplete combustion of carbon monoxide and one other product, which is water. So C10H22 plus O2 goes to CO and H2O. Balance it 10, 11. Oxygen, wowzer. 10 and 11. 21 divided by 2, 10.5. Something like that. There we go. Kind of feel like I want to check that. Have I missed a question? Name it. Ha! I missed a question. Lol. Despite enthalpy being in unit 2, why does it come up on unit 1? Rear, is this just because it's an old spec? Does the dot on the C need to be on the side with the C? No, it doesn't have to, Karen. It can go on the end, but only in equations like that. Oh, actually, it doesn't really matter. They don't care. It's because it's old spec, Rear. Yeah, sorry about that. Oh, I've got to name this now. 1, 2, 3, 4, 5, 6, 7. Trimethyl. 2, 2, 2, 4. Trimethyl heptane. There we go. Write an equation. Decane can be cracked to form a mixture of butane and 2 different alkenes. C10H22 goes to form butane, C4H double it and 2, and then 2 different ones. I've got to get to 10, so 6. So C2H4, there's ethene, and C4H, whatever's left. Alkene, 8. There you go. That should add up. I think it does. Explain why geometrical isomerism can occur in alkenes, and why alkenes produced by cracking may not have geometrical isomerism. Huh, that's fascinating. In alkenes, the carbon, and yes, you've got to write it out. Carbon-carbon double bond cannot rotate. Alkenes such as ethene produced in cracking, no idea if this is right, produced in cracking have the same atoms on both carbons, so don't show geometric isomerism. What a nightmare. What does it want for you to write that? I'm starting to run out of steam here, folks. There's no rotation, restricted rotation on the carbon. There are geometric isomerism only if there are two different groups on the carbons. Ethene, there you go, got the same two atoms on it. That's exactly, alkenes such as ethene produced in cracking have same atom attached on each carbon, same atoms attached. That's hot. It's just long-winded. Attached to each carbon. It's just long. Draw the structure of the trans E isomer produced in cracking in D. Ooh. Butene. And they want the E. E. Do you know what? No, I'm going to draw it out properly. I don't trust them. Draw it out in its entirety. There you go, butene E. Yep. Next. This question is about an alkene. Describe in detail the structure of the double bond and hence explain why alkenes are more reactive than alkenes. Holy moly, pi bonding, folks. This was covered in my webinar that I did with Winkit. I don't think he was there, though. Winkit, why didn't you come to my alkenes webinar, huh? Between the carbons in double bonds, there is a sigma bond, direct head-on overlap of orbitals, a sigma bond and a pi bond. Pi bonds. I saw Julian's message 5 hours after it was sent. Sigma and a pi bond. Pi bonds are regions of high electron density, so can be attacked by electrophiles. Alkanes only sigma bond. Ugh, I'm running out of steam. Let's check the mark scheme on that one. Be nice to see it. Head-on overlap, they actually wanted it. There is head-on overlap or orbitals in the sigma bond, sideways or parallel, or p orbitals are parallel, so overlap in pi bond. Yeah, they're pi bond, more easily weaker, or region of high electron density, bond allowed attack by electrophiles. Yay, allowed diagrams, love it. So they did want me to go a bit further than that, but I'm not going to bother making adaptations now. Am I nearly done with this? Am I at the end? I think I am. I'm on the last 2 pages. State why the amounts of each product are not equal. Oh, sorry. Hydrogen bromide, mixture of propane and 2-bromo. Draw the mechanism for the formation of the major product showing. So we've got, right, so this is unsymmetrical electrophilic addition of alkenes. Here is propene. And we're using hydrogen bromide, HBr. Show my deltas by first step. From the middle, I want to focus here, guys. Look at where I'm starting. Yeah? To the carbon, and then from the middle to the Br. Right, major pathway. I'm going to form the more stable carbocation. Going to produce a secondary rather than a primary because the secondary is more stable due to the positive inductive effect. And then the Br minus hops on, and I'm done. Finished. State why the amounts of each product are not equal. Secondary carbocation is more stable than primary carbocation due to positive inductive effect. Positive inductive effect. Next, write the equation for polymerization of an allyl bromide showing the structure of the polymer. Ew, that's horrible, isn't it? So they've given us 3 bromo. All right. Oh, don't like it. Oh, don't like that either. There we go. N, because it's a polymer. Yeah, and then I'm going to form there we go. Check mark scheme on that one. What exactly do they want? There we go. Yeah, it's just fine. I like it. Next. And I think that brings us to the end of the paper, folks. Woo! Blimey. That was an hour and 20 minutes. That was a long webinar. I'm so sorry, folks. I just didn't think it was going to take quite that long. Hey, guys. Thanks for hanging in there. I know it's been a long webinar, that one. We've been on, yeah, for something like an hour and 20 minutes. That's been a long one. I do apologize. I will leave you be now. Guys, I have sent you a document that I need you to fill in. I'm having so much fun. Oh, yeah, sure, Ria. Thanks, though. It's very, really nice to... I can't... Are you being sarcastic? I can't tell. I feel like you're fibbing. I hope you found the review useful, guys. I really did. You know I wouldn't do these unless I saw the value in it. Thanks for coming along. Can you fill in the details? I'm just going to quickly share my screen again. Yeah, I'm just going to quickly share my screen again. I've shared with you the document. I think most of you have seen it. Yeah, I shared this document with you. I'd really, really appreciate it if you could fill that in for me, guys. I'd really appreciate it. Just for the percentage that you got for paper 1, paper 2, and paper 3. Yeah, when you get the time, add it all up, lob those in. That'd be really, really useful. Thank you. Guys, I will leave you be. Have an amazing rest of your day. And I'll see you guys tomorrow. 2 o'clock, paper 2. I might have to split it in half, though. Guys, I'll see you tomorrow at 2. See you later, guys.